Got the live stream buffering. We're still in workbook volume 1 at the first half today. And I think somebody said, oh, let me pause this. So we're approximately problem 650, page 116. Thanks, Jules. 658, yeah. All right, and so one of the things that we're wanting to talk about today, well, maybe I'll just put up a list here. I want to talk about cars on curves, cars driving on curved stretches of road. We'll probably talk about some more circular motion forces, some neat examples, and then hopefully end up with fictitious forces. Fictitious. Oh man. How about I just say fict forces? That way I don't have to try and remember how to spell. Not my strong suit right now. And then if we finish all that, we're going to go on to chapter 7, which is work. The physics concept of work. All right, that's our goals for today. So it's kind of a lot. All right. So, and actually, before we get too far onto cars driving on roadways, I wanted to show you something here. In particular, and it's going to seem a little strange. Let me get zoom on it. All right. Let me move this out of the way for the zoom. Set this over. All right. So imagine you have a car driving on a roadway. Hopefully we're on, yes. And then right about here is, right about there is good. All right. Imagine this is a tire. You're in a car driving on the road, and this is the tire here. One of the things that's very confusing about this is what kinds of friction are involved with a rolling object. We're going to learn more about this later, and parts of it we're going to gloss over. I just want to try and clarify the different types of friction. Now imagine if I just slide this tire like this. I could slide it forwards, backwards, this way or that way. Imagine I was just some giant beast that could move the car around and just drag this tire around and slide it all over. You would agree that there could be some type of sliding friction. That's the type we've been talking about already, the mu static, mu kinetic, things like that. What's a little bit different with a car driving is, imagine this car is driving on the road. You could imagine this towel being like the surface of the roadway, getting crushed and then uncrushed as you roll over it, right? Or you could even think about the tire itself getting smushed and being unsmushed and springing back as it moves around. So there's actually a type of friction associated with that smushing and unsmushing. It's a very complicated type of friction that fortunately we're going to ignore. But I want to try and draw a picture on the board here for you and discuss this. Okay. If we want to try and understand cars driving on curves, I feel it's worth spending just a minute on this. So imagine, let's kind of make this over dramatic. Imagine the tire is partially flat here. So, right, this is the hub or something, right? So we've got this tire, and it's constantly smushing and unsmushing. Very technical terms, huh? That type of friction, the type of friction associated with the smushing and unsmushing, is called rolling friction. All right. And I'm going to say this effectively opposes motion. So if the car is moving this way, this rolling friction is effectively pointed opposite the motion. For our problems, we plan to ignore rolling friction. If it helps you understand how this might be negligible, one of the reasons trains, right, are so efficient at shipping materials is they don't have tires, they have steel wheels. There's much less smushing and unsmushing. And any smushing and unsmushing that does happen is more elastic. It conserves energy better. So there's less rolling friction if you use steel wheels rather than rubber tires. Obviously, there'd be a less comfortable ride. So there's pros and cons, and obviously trains, you have to build a special road for them so they don't go, so they don't crash. But effectively, when students hear friction, you usually think friction opposes the motion, right? Well, we've seen a couple of cases where sometimes friction causes motion. And in this case, rolling friction does oppose the motion, but we're going to ignore that. So basically, imagine all of your tires are super inflated, so they barely smush at all, okay? Is everybody okay with this fact? All right. Now, we also saw, we could have sliding friction, which is something like F could equal mu kinetic times N, or F is less than or equal to mu static N. These were the types of sliding friction. And as if this isn't crazy enough, I'm going to try and show you something here with this paper towel again. Let me go back to that. We're going to ignore the smushing, so we'll get rid of our smushable road and smushable wheel here. And actually, maybe I'll do this one. Okay. So we're going to learn much more about rolling motion later. But right now, Jules, am I on? Yeah. Okay. And actually, I'm going to zoom out just a little bit so I have a little bit more room, a little bit more travel here. And it looks like I can go right about here. Yeah, that's pretty good. Okay. I want you to watch this red marker carefully as I roll this across, right? In particular, right about now, watch the red marker, okay, as it gets close to the bottom. So right about here, we're going to, whoops, right about here, well, whoops, right here. Now look at that red marker. I don't know if you can tell or not, but how much do you think the red marker is moving right as it gets close to the ground? Watch it. Which way is it moving right now, approximately? Up, down, left, right? It's actually moving almost straight down. Watch it carefully. As it gets close to here, I think if I start right here with the marker up, watch the red marker when it gets close to my finger. Do you see it's basically moving straight down right now? Almost perfectly straight down. Watch right after we pass the bottom. Now which way is the marker moving? Ready? Now think about this. This is crazy. We just saw for an object where the wheels are rolling. We're going to discuss this more later, but look at this. The motion of the edge of the wheel, if this is our wheel and we imagine this is the edge, it's coming down here like this. And this point on the wheel is moving in this manner. We kind of saw that. Now I'm going to show you one more time just to make sure you believe this. Sorry if you're bored. This to me is a tricky thing. It's a huge deal in mechanical engineering. Just kind of watch the path traveled by this marker and see if you believe this. Ready? I hope you agree, kind of takes, whoops, where we go here? This practice. Are you okay with that? And if you want, we could actually roll it here. We'll do that in a couple of chapters. But for now, right here, the initial, it's not perfectly straight down, but it's almost straight down. Right here, V final is effectively straight up right after that. Agreed? So at this point, what's the velocity in between there? At the instant that it contacts, what's the velocity as it contacts? Think. Before the velocity is negative j hat, after the velocity is positive j hat, what does it have to be at the very point of contact? Zero. Wow! Think about that. The tire isn't moving when it touches the road. Isn't that cool? What type of friction applies? Static. Isn't that crazy? Think about that for a minute. You're driving at 80 miles an hour because you want to use up your gas, all right? Or 50 or 20 or whatever. As long as you're not doing a burnout or as long as you're not driving on ice and the wheels are slipping, the bottom of the wheel, the part that's touching the road, is not moving relative to the road. Crazy, right? Now, we're going to learn more about this later, but basically, you've got this rotation plus a translation. To really understand this, we need chapter 10. All I wanted to point out is, when you hear me talking about static friction for a car driving 70 miles an hour, it's not wrong. It's just the point of contact with the tire is not moving. Is that cool? That's why we can use static friction.
It wouldn't move otherwise, would it?
Yeah. So if it'd be like
It'd be like spinning your wheels in mud.
exactly. If you're spinning your wheels in the mud, the wheel is moving relative to the road, so you don't move. You need the wheel speed to match the road speed. And guess what? Later on, we'll learn, if you know the RPMs of your car, we know it's not your omega, it's our omega. If you have this road speed and the radius of your tire is this, you need your tire RPMs, or radians per second, to be that number. Anyways, we'll learn more about that later. Okay, so is everybody okay that it's fine to use static friction on the tires of the car? That's what this goal was. Okay, now take a second to read 659. I'm going to get it written up and erase the board. Okay, 659. Dom, anything you want to say about that, or should we leave it for later?
Roll without slipping.
Rolling without slipping is important. It's in chapter 10. I'm erasing the board on Zoom, so you know. I'll be right there. You guys did awesome on that. Well done. That is a hard thing to understand. I'm impressed that you guys are trying to get that. All right. So now, hopefully this problem will make more sense. Imagine you're a civil engineer and you want to understand roadways, right? This is going to be helpful to you. What problem is this? 659. Car on a flat curb. All right. So in this case, you're going to see me draw a rear view and a top view. I feel it's very difficult to understand this problem without both images. I also find it funny that the rear view shows the front of a car. So this is someone going in reverse around this. But whatever. That's supposed to be the car. All right, whoops. We'll just label this car so it can actually read it from the back of the room. And here's the center of the turn. I'll call this center axis of turn. So imagine this car is going around this way. From the top, the axis would be coming out of the page, and the car would be over here. It would look like a box. And this car might be moving this way with some speed v. And I guess I could try and draw the actual road here. So imagine this car is driving on a circular track like this. So does everybody understand the pictures okay? All right. Tell me one force acting on the car. MG. Which picture is easier to draw it on, in your opinion? The rear view or the top view? The rear view. The rear view. So that's why it's kind of nice, right? Here we can see the circular motion better. Here it's easier to draw the forces. Do you understand why I'm drawing two pictures now? Okay, so we got MG. What is another force acting on the car? Normal force. Which way? Up. Yep. Now, this car is moving in a circle. Remind me, and it's moving at constant speed. Is it accelerating or is it not accelerating?
It is.
It is accelerating. Remember all this, when the V changes direction, you're accelerating. So even though you have constant speed, right? It's first this way, then that way, there's an acceleration. Which direction? Towards the center. So do you agree it's accelerating this way? If we have constant speed, we can't say that AC is equal to 0, but we can say which component is 0? A tangent. Excellent. So constant speed does tell us this component of acceleration is 0, but it doesn't say acceleration total is 0. Nice job. Well, I'm going to look at this force, this picture right here. If it's going to accelerate to the left, we need a force to the left. What force keeps the car in circular motion?
Friction.
Friction. Which way does friction point?
Towards the center.
Exactly. If there was no friction, it would keep going in a straight line. If there wasn't any friction, it would just go straight and it would feel like it slides to the outside of the curve. But in reality, it would just be going straight, right? There was no friction, there'd be no acceleration, it would just go here. We do not want that. This can happen if the road is really icy. We do not want that. What is the force that pushes the car to the outside of the turn?
There's not.
There isn't one. Good job. We feel pushed to the outside of the car. We're going to discuss that later today when we talk about fictitious forces. Okay? You feel pushed to the outside, but that's only because the car is saying, dude, if you want to go in this circular motion, you better turn. So the car is pushing you towards the center. You feel pushed to the outside. All right, whatever. This problem's easy, right? At this point, it's the same as we did this problem about 6 times last time. The main thing that we've seen in all of these problems is make sure you remember it's accelerating towards the center, even if you're at constant speed. We see the normal force and friction at right angles. Oftentimes they're switched like this or that. Okay, so far so good. Let's read the question now.
Either radius or the
And so look at the question. Good question. This one says, determine the minimum turn radius for this car. So I think that's what we're trying to figure out. Excellent question, right? So our goal for this problem is determine minimum radius if car at speed v. Got it? So you're right. Usually we're going to be talking about the radius, the speed, things like that, and friction. Did this problem tell us the frictional coefficient? What were the givens? Let's just make sure we know what our givens are. This is a good trick to do here. Look in the problem and tell me what's given. Is the mass given? Did I ever say m? Okay, what about mu static and mu kinetic?
Coefficients of friction between the tires on the road are mu static and mu kinetic.
And then we know v, and I'm assuming we know g. I haven't built many tracks on the moon or Mars lately, so I'm assuming we're doing this on Earth. Okay. I see this right here. Minimum radius. That gives us a special piece of information in this problem. What is it? We're at the minimum radius for this speed. This is sneaky.
AC?
No?
No.
Well, let me ask you, right? It's saying something about the minimum radius here. What if you made a radius even smaller? Would this car still be able to execute the turn if we tried to use a radius smaller than the minimum? What do you think?
It would slide.
It would slide. Therefore, the minimum radius implies
Static friction.
more. Any less, it would start to slide. Therefore, it is on the verge of flipping. Oh my gosh, isn't that cool? Did that make any sense? Sleeping. Whoops. Freudian slip, on the verge of sleeping. Man, this class is bad. Sorry. I don't know what was going on there. Oh, did this make any sense? If we're on the minimum radius, remember I was telling you to look for those keywords and problems, minimum, maximum. Those are oftentimes clues that we're on the verge of slipping. In this case, that fits that mold. Everybody okay with that? Yes, no, thumbs up, thumbs down. All right, all right. Hey, okay, if we're on the verge of slipping, what's my frictional condition?
Equals to mu s then.
Mu Sn. All right, what should I do next? Force equations. Okay, give me some force equations in the centripetal direction.
AC plus half equals MAC.
AC is not a force. Do you agree? So let me rewrite this just to be clear here, because it's been a while. Sum of forces in the centripetal direction equals mass times acceleration in the centripetal. All
So
right.
just force equals MAC.
Which force?
Friction.
Yes. Remember, this is just the forces on the block.
Okay.
And then the AC has to come on the other side. Good job. Good job. Positive or negative for friction?
Positive.
Exactly, because friction is towards the center, and we're doing towards the center forces. Excellent.
That's what the little C means.
What's that?
What's the C colon?
Oh, that just means centripetal direction.
Okay.
Okay, so that's a good question. When you see me write C, I mean, that's my way of saying forces towards center. Good question. Sorry about that. Is that better? Yep. Okay, wait, you said it's F equals M AC. All right, well, we're at it. What's a good name for this direction? Is that the tangent direction? That's not tangent to the motion. It's tangent to the circle, but it's not tangent to the motion. So what I call this tangent or Z. That's the Z direction. So if it helps, I could draw a coordinate system like this. This is towards the center. This is the Z direction. Sometimes it's nice to have that coordinate system, isn't it? Okay, in the Z direction, what are the forces?
Force and,
Are they balanced or not?
they're opposite of each other.
Yeah, they should balance in this case. Are they an action-reaction pair?
No.
No. Okay, good. Nice job. Yeah. So I could just write N equals mg. All right. What were we trying to find? Remind me.
The radius
Radius. I don't see it. Where is it?
in AC.
in AC. What's the equation for AC?
V squared over R.
Why would you use V squared over R instead of R omega squared for this problem? Because the given was V. You know what I'm saying? So if the problem is asking about V or it gives you V, use V squared over R. If it's asking about omega or period, I would use R omega squared. If you forget what AC equals, how do you find it on test day?
In the back.
On the equation sheet. Yeah, back of the book, but on test day, it'd be on your equation sheet. Yep, good. All right. Take a second, crank it out, solve for R. I'm going to rewrite over here and then just kind of start up again. You like the color coding or not?
Yeah.
All right. I know not everybody can see it, but I'm just switching boards now because I ran out of room. What do you think I'm going to do with that cap or with this lowercase f now? What do you think I'm going to do? Yeah, mu-sn, because that's allowed. Let's get it in there. If it's allowed, geez, you want that in there right away. Okay. What technique should we use to get this? If we're solving for R, what might you do next? Oh, you could.
Do you switch the R and the
What would Horatio do?
Take a ratio.
That Horatio, there's a little Horatio in all of us. That's just faster. Now, that doesn't mean you couldn't have done what you had said. Both of you had great ideas. I just like the ratio in these types of problems. It comes in handy. It's pretty easy to screw this up. Imagine you're on a test day. You're stressed out. Why don't you just take a second to rewrite this before doing any more algebra? Because now I can see this is V squared over R all over G. Right? It's just a little bit easier for me to read now, and I'm less likely to make a typo. This side, I could say that's V squared over RG, and now I'm off to the races. R is equal to,
V squared over mu SG.
yep. Now let's think about this. I know this seems pretty silly, but we're finally seeing something that could be useful in the real world. You're a civil engineer. You buy some land because you're going to build a ramp or a turn in a road or something, right? Well, if you know you want people to drive 65 miles per hour and you know typical coefficients of friction on bad weather days with rain, that would tell you how much land you need to buy, because you know the minimum radius of the turn has to be at least this, and you probably need to make it at least twice as big to make sure people don't kill themselves every day. So, or said another way, what if you're like, you know what? I've only got so much land. I know the size of the turn. I know on a rainy day or icy day what this number is, and I know this number. I can put up a yellow sign that says, dude or dudette, drive at this speed or less so you don't kill yourself. What do you think?
Or you could do a bank.
That's probably harder. Do you think we're going to do that? What's the next problem in the book? So we see that, man, this is cool, but what if we want to bank the turn to make it safer? Let's analyze that situation next. But is everybody okay with this problem? What type of friction did we ignore?
Squishy.
The squishing and unsquishing, the name for that type of friction was called rolling friction. It matters. That basically reduces your gas mileage, as does air resistance, right? So that type of friction matters a lot. If you have big knobbly tires, you're going to have more rolling resistance. If you have bald tires, you'll have less rolling resistance, but you'll also have less traction, more likely to slip. Trade-offs in life. Okay. Should we start up? Any questions from Zoom either? And just so I can do this one, I want to make sure I get this all on one board here, just for a second for the Zoomers. There we go. All right. So that's the full problem there. All right. Are we ready for the next one? Let's do it. What is that? 660? Okay. So let's do 660. I'm going to erase the board and catch up. You can work with your neighbor. Talk as much as you want. I think that's a cool problem. Did you notice that's basically the same problem as which flies off first? If you didn't, it's basically the same thing. Kind of cool. Smushy and not smushy. 660. There's some center of the circle. Okay. And then there's a rear view. Maybe this is a van delivering donuts. Can you briefly show me with your finger which way in this rear view is the center of the circle? Is it diagonal, straight over, diagonal down? What do you think? Let me see. It's straight this way. Do you agree? The center of the circle, even though the car's angled, right? The center of the circle is over here. Let's do this in purple here. So the center axis of the turn is here. It's going around like this. Can you visualize this for a second? Think about this. Remember the conical pendulum, the ball on a string that was tracing out a cone? Do you see how this is the same thing as that? It's upside down, but it's basically an inverted conical pendulum. Do you kind of see it? All right. Right now, before we do anything else, if this car is moving at constant speed, is there acceleration?
Yes.
What's constant speed? What's the acceleration if we have constant speed?
AC.
AC equals v squared over r. What's a tan?
0.
Okay, so we have no tangential, but we do have AC. Which way does AC point in this picture that I'm pointing at right now? Radially inwards, AC. Which way does it point here? The same way, this way, agreed? Now, draw it a little bigger than you think you should. Make it really big, okay? Just trust me on this. Make that arrow really big for a second. Okay. Now, what is 1/4? Oh, and let's read the question now. The car hits a patch of ice. While on the ice, negligible friction force. Car hits patch of ice, basically mu goes to 0. No friction. Does that sentence make sense? We've got no friction. If that is the case, tell me one force acting on the car.
NG.
mg. Which way?
Straight down.
By not rotating our coordinate system, it's easier to get mg right. If you start doing stuff where you twist your paper, that's when you start screwing up mg. Another force, someone else. Normal, which way?
Perpendicular to the axis. Straight.
Perpendicular to what?
The axis.
Perpendicular to the incline or the plane. The axis I want to call this. So
Okay.
you see what I'm saying? Yeah. But you're right. Perpendicular, you had the right idea. I just didn't know what you meant. Let me ask you something. Well, let's do this first. In this case, we could choose a lot of different coordinate systems. 2 of them jump out. Right? Do you agree we could do a standard XY coordinate system? Do you agree we could use a rotated XY coordinate system? Now, they both have pros and cons. In this particular problem, do you think we should use a regular coordinate system or a rotated, and why? Why?
I'm more familiar with it.
Oh, okay, that's true. That's a great reason. He said, I want to use a regular coordinate system because I'm more familiar. What?
I'd say regular because AC will be like
AC lines up on regular and G lines up on regular. How many things do you have to split up if we use a regular? 1, the normal force. If we use a rotated coordinate system, what are the pros and cons of that? Well, I'd have to split up mg. Is there anything else you'd have to split up if you use this coordinate system? You'd also have to split up that. Now, to be fair, this particular problem has no friction. If you did have friction, which way would it point?
AC.
I don't know is the correct answer. It might point up the ramp, it might point down the ramp, but do you agree it would be along the ramp? It could even be 0 if you're at the ideal speed. So in that case, if you have friction, suddenly maybe it makes sense to use a rotated coordinate system. Plus, we've done blocks on an inclined plane over and over and over until we puke, or, well, you should have. Whoa, this focus is going weird. Did it just do that? Let's do this. Sorry. Weird. All right. Sorry about that, everybody. On Zoom. That was strange. All right. So, but yeah, there's times we're going to want to use this. There's times we're going to want to use that. My claim is, why don't we do both of them so you learn how to handle it either way? Are you cool with that? Because I'll explain later. There's times you want to know both. Okay. So let's start with the standard XY coordinate system. Okay. Technically, this is not a free body diagram because I still have the road in there. So I'm going to draw it a little bit over here. There's a normal force up. There's mg down. And then we're going to use a normal coordinate system like this. A normal XY coordinate system, excuse me. And then I guess I could draw that here. Maybe I'll use this way is center. This way is z, because it's not tangent to the motion, right? Or, well, yeah, it is, but discuss that. We know AC is going this way. This seems like the best coordinate system for me for this problem. What's an issue that we are faced with right away? What's this angle? How could we figure that out? What's that?
Look at the diagram.
Look at the diagram. So it's handy to have this diagram. Remember, we want to do our geometry over here so that we have a nice clean FBD. All right, help me out. Oh, you might really like this, everybody. This is probably something you should pay attention to really closely. Watch this. I'm going to put on this coordinate system in here. Right? And now I don't know if you can see this. Maybe I'll draw this a little bit better here. I want you to memorize this for the rest of your life, okay? We know this angle down here is theta. We've got some other forces here like this. What's this angle right here? 90 minus, good. What's this angle right here?
Theta.
What's this angle right here?
Theta.
Opposite whatever geometry rule. What's this angle?
90 minus theta.
What's this angle then? This is a right angle, so this is theta. Well, what's this one? Whoops. Oh, there we go. And then I guess if you really wanted to, take a look. We could even back project this normal force here. What's this angle in here? Theta. So what's left for this one? Take a look at this pattern. Do you see that every other angle is theta? Every other angle is 90 minus theta. Never forget that, ever. Got it? It just comes up a lot.
That would have been useful in the last test.
Would it?
You have the one of the problems had something pointing down like this, and I set up my triangle wrong.
Oh,
for the
shoot.
for the cross product and dot product.
Yeah. Okay. Oh, I see. Okay, we can talk more about that later. I'd like to look at that and see what you're thinking. Yeah, because that, yeah, I don't know. This is pretty useful though, isn't it?
Yeah.
Here's the other thing. Now, Dom and I think are in agreement. One of our pet peeves is when students draw every single angle as 45 degrees for no good reason. Am I right, Dom? Or not?
Someone just drew a angle on their homework, which was supposed to be 60 degrees, less than 45. How can you understand which component of the vector is bigger if you draw the angles wrong?
It's very difficult to understand problems if you're always drawing everything at 45s, or basically, I think, now this is for me, and Dom can confirm or deny afterwards. If an angle is supposed to be less than 45, make it obviously less than 45, like 20 to 30 degrees or something, 15. If it's supposed to be more than 45, draw it obviously bigger than 45. Even if you're only that good, usually that can help you a lot. Like Dom says, you can tell which component of the vector should be bigger. Would you agree with that statement, Dom, at least as a bare minimum?
Yes.
Ideally.
Closer to 0 than to 45.
Yeah, if it's supposed, and most raceways are not banked at 60 degrees. Exception might be a professional racetrack, but we're talking about like Prius. Yeah, we're talking about Prius and donut delivery trucks. Okay. All right. So far, so good on that. Did everybody understand this alternating angles? Now, if you are good at drawing your angles, just look at it. Does it look like theta or does it look like 90 minus theta? Is it a skinny angle or is it a fat angle? Skinny. So you don't even have to do all that work. You can just know the answer. We've derived this. We know every single other angle is going to be theta or 90 minus. So if you draw a skinny angle for theta, you look at the picture. If it's skinny, it's theta. If it's fat, it's 90 minus theta. What do you think? Good? Never forget that. What's this side of what's this component right here? What is it?
90 minus.
No, this force component, sorry. This N cosine. Notice, here's an example where the original problem gives you an angle to the horizontal, but because of geometry and reality, we see that sometimes theta ends up to the vertical. That's why I've been harping on this. Sometimes you don't get a choice in whether the angle is to the vertical or horizontal. I know you don't like it when I mess with you on test 1 that way, but yeah. All right. In this case, just to keep it on one board, I'm going to try and squeeze this in right here. I apologize that it's going to be in this little box. What are the forces in the centripetal direction? in the centripetal direction. And I think you two have been talking a lot. Yeah, go ahead.
Would the n sine beta be negative? What?
That's what I'm asking. Okay, you made the mistake of speaking up. I'm gonna puzzle you, right? It depends on your coordinate system. I chose towards the center as positive. Based off that, is this positive or negative? Okay, you answered your own question. Do you agree?
Yeah.
It's not that bad, is it? But do you agree answering the question, is it positive or negative, is impossible without understanding your coordinate system? That's why you draw this. All right. Are there any other forces in the centripetal direction? No. So this all equals MAC. All right. And then in the Z direction, what do we get? Somebody else. Maybe somebody new. You want to give it a shot?
M cos.
Yes, yes. Exactly, minus mg, and what's it going to equal?
0.
0, right? Because this car is not accelerating off the plane here, right? Nice. Do you agree I could flip that around like this and make that mg though?
Yeah.
Outstanding. Nice job. If we were looking to analyze this problem, well, maybe we should read the question now. Agreed? What are we trying to do? Determine what in part B? We did part A, FBD, force equations. What's part B? Speed. I don't see speed in here. Where is it? Where is it hidden? We're looking for speed. AC. See the pattern that we're doing? Basically, we do a circular motion force problem. Write down some equations. I tell you some variable to solve for and see if you can do the equations right, get the frictional condition right. What technique might you use to solve this problem? What might you do next? Why would you do that? What drops out?
The n to the n.
Got it? Okay. I need to go to the other board. So now, bringing this up, when I take a ratio, rewrite it. Oh, cool. What do you get on this side? Tangent theta. Sine theta over cosine theta is tangent theta. You are expected to memorize that. Okay. What do you think? Are you good with that? Something special about this now. This was the ideal speed. Oops. Okay. We see that no friction is required, right? If this is an icy road and you happen to be going at this exact speed, now this would be tough because you'd have to know the angle of the incline, you'd have to know the radius, all right? So at G, you could probably use 9.8. You could do this. And now I want to be clear here. Help me out. When I say friction, what type of friction am I talking about? Rolling or sliding? Sliding. Remember, we're ignoring rolling friction all the time, right? I don't need sliding friction. Basically, mu x, right? How about I say mu s can be 0? So to be clear here, sliding friction or mu s can be 0. Obviously, mu is not friction, but it relates to the friction as we've seen. Are you clear with that statement here? Friction is F, mu is the coefficient of friction. This, I know this might be boring you, but think about it now. I want to go back in time to like 2 or 3 classes ago. Remember when we were talking about a block and we said, first set it on the verge of slipping and we can find a condition. Remember there was some block and we said, oh, if you pull with 4.91 newtons, it's going to slip. But if you pull with 4.9 or less, it's not going to slip. Remember when we did that? Friction is tricky, right? There was different ranges. Well, now we see something. If you're going too fast, by that I mean faster than this speed, do you think you would tend to slide towards the outside or to the inside of the track? If you were going really fast, you think you would slide towards the outside or the inside of the turn relative to the turn? Did anybody say it? I couldn't hear. Yeah, remember which flies off first? If you don't have enough friction, there's not enough friction to stay in the circular motion, you slide outwards relative to the turn. So think, if you're going hella fast, which way would friction point? Up the plane or down the plane? If you're going too fast, you tend to go this way, therefore friction is. What if you're going too slow? If you're going too slow, think about this. If you were at rest, what would you tend to do? Slide down the plane, therefore friction is up. So for slow speeds, friction is up the plane. For fast speeds, friction is down the plane. How do you know what's slow or fast? Set friction to 0, figure out the ideal speed, things faster than the ideal speed, friction down the plane. Did that make any sense? All right. Okay. Now, I know I promised you we would do this with the other coordinate system. I know you don't want to do that, but let's do it anyways. Okay, so I'm going to draw this free body diagram again. We don't need to do the whole derivation, but I want to show you the other coordinate system for a reason. Let's just do it. Let's stop the talk and get the rock here. We had, and draw this picture a little bigger than the other one because you're probably going to be bad at it the first time you do it. Draw it a little bit bigger than you think you should. Kind of big on the page, like a quarter, maybe a third of the page. And in particular, I want you to put AC over here and draw AC bigger than you think you need to draw. A lot bigger. As big as one of your arrows, okay? Now, I want to use this coordinate system. And I want to use the same coordinate system for AC. See that? And in this case, I'm going to call this direction parallel, or just parallel. I'm going to call this direction perpendicular, or the perpendicular symbol. Is everybody okay with that? And yeah, getting this diagram right, hopefully will save you headaches later. Okay, so it's worth it to do it right, ask lots of questions, slow me down if you have to. Does this picture make any sense? And maybe let's make the down the incline. Let's make this way parallel. That way it looks the same as this picture right here. Parallel and perpendicular. Okay? Sorry about that. We've got parallel, we've got perpendicular. Which vectors need to be split up in this new picture? MG and AC. Now, we know from experience, this angle down here is theta. What's this angle? What's this angle?
Theta.
Theta. Well, what's this angle? If this is theta, what's that angle? This is also theta. All right. I'm going to do something incorrectly and I want you to watch so you don't do it. This isn't going to split up that triangle correctly. Do you agree? Because this is not the hypotenuse anymore. The original vector needs to be the hypotenuse. That is not a correct splitting of that vector. I need to do it this way. Now, which way are the arrowheads? This matters for us. For AC, on this arrow right here, should I put the arrowhead right here or down here? Up top or down low? Down low, right? Because it's going down this way, and then to get up to here, which way do I need the other arrowhead? Down low or up top? What is the name for this component? AC
Cosine.
cosine. This side would be AC sine. What's this component right here? Totally wrong. Agreed? Right? Okay, nice catch. Nice catch. Thank you. Well played. Okay, so then the hypotenuse is the longest part of the triangle. The hypotenuse is the original vector mg. This is going to be mg cos. This is going to be mg sine. So far, so good. All right. Let's write down forces in the parallel direction for no good reason. So this means forces in the parallel direction, not 11 colon. Forces parallel. Let me write that. Forces para. Who's feeling brave? Michael, go for it. Sorry, I looked at you first. Give me one force that, and we're calling this way positive, okay? What's one force in the parallel direction? Correct. Positive or negative in this case? Correct. Is there anything else going this way in the FBD? No. So then I write equals M times what?
AC cos.
AC cos. Do you agree? If you could do this, you could do dynamics. You can be an engineer. If you could be patient and work through this and understand this, you can do it. You may not like me. I don't care if you like me. I just want you to build safe bridges that I can drive on. You know what I'm saying? But so, right, we're getting to that point where you're kind of like, you know what? You guys are not worthless anymore, right? You can actually do something useful. I love it. Okay, let's keep going. Perpendicular direction. Somebody give me a force. And positive or negative? What else? Could I just say equals mg cos in this case? What's that?
Yeah.
No.
Oh wait, no, because you have.
Yeah, I tried to trick you and I got you. You see it?
Yeah.
We're so used to saying, oh, these forces balance. Look, they don't balance because there's an acceleration there. You see that? Oh. So the trick of saying the ups equals the downs is a good one, but it's only valid when it's valid. Here it's not valid. So help me out. Tell me the equation again. Go for it.
Mg cosine.
Mg cos equals.
AC.
Nope.
M.
Yes. And then I'm going to run out of room. You see my pieces of tape up on the board telling me when I'm going to run out of room? It's like, oh, I can never go. Oh, come on. Oh, jeez. Is that still visible, Jules, or am I zoomed out too much? Good enough?
Yeah.
Thanks. What is this? AC Green? Former Lakers player? Oh, wait. Yeah, I'm a Kurt Rambis fan. Nobody knows Kurt Rambis. Does anybody know Kurt Rambis? Okay, I'm old. As if we needed that. Okay. Now, at this point, this looks ugly as crap. Do you agree? Can anybody think of a reason we might actually want to use this coordinate system? In particular, does anybody see one special parameter that's actually easier to understand with these force equations? Look carefully.
The normal force?
The normal force. Think about it. I haven't, like, normal force doesn't appear in both equations. It's actually fairly straightforward to understand the normal force. If you know the velocity, the angle, and the radius, you can get the normal force like that. Cool, right? So generally speaking, I'm going to go big picture here, literally on Zoom, big picture, with my remote, which I lost. Where? Oh, right here. Nice. I know this is going to sound crazy. Look at this. We've got two styles, these two, right? And maybe I could zoom in just a little bit so they can see better. All right, let me just get this. There. Look, if you were trying to understand the velocity or the radius, by all means, you would want to use the normal coordinate system because that pops out all by itself and we don't have to split it into components. If you were trying to learn something about the normal force or perhaps friction, right? Friction would appear up here isolated, normal force down here. So if you were going to use friction or the normal force, you might want to use this coordinate system. But both coordinate systems should work for both types of problems. You can choose your poison. What do you think? So far, so good? All right. So at this point, I'm going to mention 6.61, 2, and 3 show you basically the three types of variations I could do on this that involve friction. You could have slipping up the curve, down the curve. You could try it's on the verge of slipping or it's not on the verge of slipping. Basically, and I did a lot of work on those showing, I think in those I did it both ways, both coordinate systems in the solutions. So you kind of try it both ways at home. Sound good? You definitely got to do a couple of those to make sure you're feeling good. Now, at this point, I want to ask you something in general. Are you getting better at algebra? For the most part, are you getting a little better at it? So think, at some point, what is most crucial to study? Obviously, you need to do some problems all the way through. You have to do a few so that you know you can do some algebra. What is worth most of the points on a test? Free body diagram, force equations. Usually that's 2/3. So if you are trying to get better at this and you're already good at algebra, do every single FBD and force equation and skip the rest. You know what I'm saying? And if you're looking around in the solutions and for some reason I left one of the equations out, you could say, dude, I did the FBD. I think they've all got the FBDs in there. There might be one or two where I forgot to write down a force equation in one direction. So you could do that very rapidly, improve your skill, right? FBD's force equations, move on. FBD force equations. So maybe you do some of the practice, do like the bare minimum, work them out. And then the rest of them, the recommendeds or something, don't do the whole problem. Just do the FBDs and force equations. Got it? Let's take a break. We'll come back. Or, yeah, let's take a break. Let's take a break. All right. 10 minutes. I got 12:11. All right. So a couple more problems here. I'd rather do a really good job on this. Chapter 6 and chapter 10 are two of the chapters that I try to focus on. So I'd rather do a little bit extra here, and basically some of the times you notice I'm kind of hurrying through some chapters. I do that so I can put a little extra effort here because I think some of these topics I have to go slower if you want to get them. That said, let's look at 6.64. We talked about cars going around bank curves and such. And I'm going to erase this because our schedule may be blown here. I don't think we're going to get to chapter 7, but we're still going to do some of this stuff. Apologies for that. So what did I just say? 6 point what?
64.
67?
64.
64? Car going over a hill?
Yes.
Okay. Obviously, you would probably care more about a car going over a hill, but it turns out it's probably easier for us to talk first about a block sliding over the hill. And in particular, one of the things, maybe you've seen this in your calculus classes, maybe you haven't. One of the things you can do is at any point on a motion, we can draw a circle that represents the path at that one spot. Now, this is not a very good picture, I know. But what I'm trying to say here is, look, this road is not circular. But at the very top, when we have a block that's this big, passing over the top, we could model just this portion of the track as being circular. Did that make sense? And by doing that, we don't have to understand the entire path. We can just understand this one piece of the path. Now, in this case, the height of the block is significant. Normally, we deal with small objects. The height of this block is supposed to be the rate. Did I use capital R?
Yeah.
So let's use the same symbols that I used in the book. Okay. We're assuming, and maybe this isn't perfect, but it's approximate. It's about right. About 4 of those could fit in there. So this is approximately to scale. If this object has some size here, that's not very well drawn. Let me draw it just a little better. This is how I like to think about it. The object is not going in a circular orbit of radius r. It's actually going in this circle. Does that make sense? It's a little, the center of mass of the block is actually a little bit off the road. So if the road is curved this much, the center of the mass of the block is actually going around in this other radius. So I'm going to use radius for the block is actually equal to what in this picture?
Radius plus center of mass.
Radius plus, and if it's assuming it's a uniform object, where is the center of mass in a block? At the middle or somewhere else? At the middle, so how much would I need to add of the height? R over 8. So in this problem, we see that if the road has a radius of curvature capital R, and this happens to be the height of the block relative to that radius, the radius of the motion, let me put this here, radius of block's motion is actually that circular motion curvature plus the half the height. So to be clear, this is height over 2. Is that okay? To be fair, on test day, I'm probably not going to do this to you, but it does matter in the real world, so I wanted to mention this. Typically on a test day, what I'll say is the height of the block is negligible, so you can ignore this little contribution. Did everybody catch that? I'm going to say that one more time. On test day, usually I say height of the block is negligible, so we don't have to worry about doing this trick. Got that? All right. Now, that said, we understand it if we need it. Look at that, though. That's a correction of about 12.5%. Okay. So that was part A, I think. What is part B asking us to do? Get what?
The normal force.
And mag, normal force mag. I don't know if I said magnitude or not, but typically, oh yeah, normal force magnitude. Okay, if that's the problem, what do you think you should do? FBD, okay, give me a force. At the top, what's one force on this block?
Mg.
Mg. What's another force? And which way? Floors push up. They do not pull down unless they're magnetic or something, which can happen, but we're going to ignore that case. This looks a little bit different than the ball on a string, doesn't it? For the ball on a string, what's the force at the top if this was a ball on a string? Tension. Which way would the tension be for a ball on a string?
Down.
Down. So remember, strings pull, floors, walls push. Got that? Okay. Let's say we have constant speed just to make the problem easy. Does that set acceleration to 0? No. What does that tell us? Two things. What is a tan? That's 0. And then AC is the total acceleration. Right? Which way is AC? At the top of the hill, which way is AC? Down? Who's feeling brave and wants to try force equation?
Mg minus n equals MAC.
Mg minus n equals MAC. I'm not sure if that's right. Let's write it down and look at it. Do these two have the same sign? Yes, looking good. What do you think? Is everybody cool with that? This is effectively what he did is he said, this is the centripetal direction. So he called down positive. Do you agree? Nice job. I don't know what we're supposed to do at this point. Do you? Oh, determine the normal force. Oh, I forgot. Oh, it even says it right there. I'm so dumb. Okay, help me. What's the equation for the normal force? Mg minus MAC? Is that right? Make sure I didn't flip something. Let's see, if I move this over, it's positive, then I move this over, it's negative. I think that's right. Do you agree? Yeah. Well, do you agree if you know V and R, we've got the normal force? Piece of cake. Let's think special here. What's going to happen as you go faster and faster and faster? What happens to the normal force?
It's smaller.
Why? Explain.
Because AC increases by V squared.
If V goes up, AC goes up, we're subtracting more and more. Can you catch air? Can you fly over a hill and lose contact with the road? Yeah. If you go too fast, that's a technical term. Oh, geez. That was a very strange noise to make. Whatever. If you lose contact, what's the special condition? Remember the bucket of water? When you lose contact, what did we say? Jeez.
N equals 0.
Excuse me, sorry about that. I shouldn't have made that second attempt at that noise. In this case, do you think that's going to give a maximum speed or a minimum speed? That gives a Vmax. Sorry. Okay, this is a lot like the cup of water on a tray, right? But there's a subtle difference. With the cup of water on the tray, did we have to worry about minimum speed or maximum speed with that? The water would come out if you went, what, too slow or too fast? Too slow. The reason that one was different, if you remember, water on a tray, the normal force was down because the cup was up here on the outside of the water. Remember that? So in this problem, we had N plus mg for water on a tray, and we found there was a minimum speed. With this one, with the normal force going out, we see we get a maximum speed. Got it? Wait a minute. What's the force required to keep this thing going forwards? Shouldn't there be a force left, right here? Did this problem have negligible friction? Frictionless hill. Good comment. This says frictionless. Thank you for bringing that up. This is what I want to say carefully. Just listen to me for a second. Give me a second. Do you need a force to move? No. You need a force to change your motion. Agreed? What I have seen over the years on test after test after test, when I put this problem on here, people will suddenly start drawing shit left and right, and it makes me want to go crazy. You don't need to have a force to move forwards, right? Imagine you just flick this thing. Well, I needed a force to get it started, but then I don't need a force to keep it moving. Now, to be fair, if we had friction, if there was friction, then you would need to have like a little rocket thruster or something. So if there was friction, we would need these two forces to balance. Or if there was air resistance or something like that. But generally speaking, if we have constant speed, A tan is 0, what does that tell us about the left-right forces anyways? If A tan is 0, the left-rights balance, yes. Did that make any sense? Watch out for this. If you're at the top or the bottom, usually A tan is 0, the left-right's balance, so we don't need to discuss the forces left and right. Students sometimes get really caught up in the left-rights, but just remember, A tan is 0, left-right's balance. Enough on that? Oh, yes.
And it's not like if it moves just a bit, it will no longer be in the circle, right? It will be like circular motion.
It could be circular motion, but it would be non-uniform circular motion, meaning circular motion, but V is changing. Are you saying as it moves down the hill? Yeah. A few seconds later, it's a different circular motion. Now, here's where that gets really crazy. You can argue this entire problem is circular motion as long as you admit the radius of the circle is changing, right? And that may seem a weird way to handle it, but that's just saying, let's use cylindrical coordinates. In cylindrical coordinates, everything's circular motion, just the radius and the angle are changing simultaneous. That's for another class, or talk to me afterwards. I can argue all motion is circular motion if you do your coordinates and allow VR to be non-zero. Remember we talked about that? Let's talk about it later. All right. Let's look at 6.66. Let me do this. Let me zoom out a bit. One of my favorites. Here it is. Hey, Angus, you back there? Come here for a sec. Everybody say this is the best demo you've seen the whole day. What do you guys think of this demo?
Best demo all day.
Yeah, see, this is the one Angus built. All the code. Yeah, all right, let's give a round of applause. Very good. That was it. That was it. You're pumping, man. We always like, oh, my demo's better than your demo. That ladder is amazing. Okay, anyways. Okay, so in this case, you could do this problem and study it. My question is, look at these two nuts. We've got the large mass and the small mass. What I'm going to try and do is get this thing spinning, and I'm going to try to change the speed very slowly, very gradually, such that A tan is approximately 0. And when I do that, my question to you is, which of these nuts is going to have a larger angle? Discuss with your neighbor while I get the string ready. Does the question make sense? It's going to start rotating, right? Like this. And when it reaches equilibrium, it's going to be kind of unstable there for a minute. My question is, out of these two, the big one and the little one, they're at the same radius. Which one of those is going to swing outwards more? Okay, discuss with your neighbor while I get it ready. Yo,
When you start spinning, can you just say let it rip?
what's that?
When you start like pulling on like make it rotate, can you just say let it rip?
Let it rip? Is that something I should know?
Have you ever like heard of Beyblades?
What?
Have you ever, like Beyblades?
I don't know what that is at all. Bait? What bait lights?
Beyblades.
I don't know what that is. You'll have to tell me later. Let's get to the demo. Yeah, you can tell me. Dude, I don't know anything. All I know about is walking around the woods and drinking beer. That's it, man. And I know a little bit about blocks on planes. You know what I'm saying? All right, so yeah, I know nothing. I'll learn later though. Okay, let's take some guesses. What do you think? Which one's gonna fly out farther? Little one, big one, same. What do you think? I hear a small one. Anybody? How many? Just raise your hands. Just what do you think? Couple. Okay. How many think the big one? Couple. How many think the same? All right, let's take a look. Now I got to pull this at a very gentle rate so that it accelerates with A tan. Ready? A tan approximately 0. Whoa, I'm going to get hit in the face. Which one flies out farther?
I can't tell.
It's the same. It's the same. Now think about this. When you go to an amusement park ride, we don't have to worry about kids getting adults, right? You know what I'm saying? Do you see it now a little bit better?
Yeah.
And then just so you can see this better, probably should have popped one of these. I wasn't thinking. If you do the FBD for this problem, what's going to drop out? Mass. What's the hard part about this problem when you're doing the FBD? We're going to have an AC in here. Do you agree? Let me get this a little more oomph here. All right. Now it takes a second to kind of stabilize, but oh, isn't that weird? So if you don't pull this smoothly, it does this wild jerky motion. All right, I should do this right. All right. Hit in the head. One more time. I don't know. I think this is cool, so I think it's worth talking about. Basically, we expect the mass should drop out, right? I don't think I need to pull it that much. Oops. Hopefully that's enough. Just a second here. Oh, Jules, is this on screen? That would be good if it would actually work, right? All right, here we go. Oops. Whoa, that's pretty crazy. Whoa, that's like a Disneyland, make that, right? As it slows down, it'll stabilize, but hopefully, can you see the strings a little bit better now? I hope so. I don't like that. At least you don't have to look at me. But, okay, there should be some circular motion, agreed? Approximately. Now, in this case, obviously this one that's in here has a smaller radius. That means it needs less force towards the center. That's why its string doesn't have to be angled. You see the angle on the string? Some of it is up. The tension force has an upwards component. Let me just freeze frame this for a second. There's an upwards component of the force to support the mg. Notice the inwards component provides the force, which gives the acceleration MAC, right? Now, in this case, what's the radius of the circular motion? This. Do you see it? It's going to relate to this radius plus L cosine or L sine theta from the, remember that?
Yeah.
So in this problem, one of the things that's tricky is figuring out the radius from geometry. My trick, don't draw the FBD, do your geometry on a separate picture than your FBD. Did that make sense? Basically, figure out all your radii and lengths on one picture, figure out all your forces on its own picture. Good? Oops. Let me show you one more that's kind of cool. Look at the next one on the next page. You guys can do that one at home if you want. We're going to do it. This is a cool one. Okay. I might be able to go in. Jules, let me know if that works. Can you see the whole thingy on there? Okay, thanks. About there? Thanks. Okay, nothing up my sleeve here. That's pretty good. Now, is that showing up okay? Thanks, Jules. All right, so now I'm going to spin this thing, right? Now you can tell from the picture in the workbook what's going to happen, but I want you to think about this. Maybe skim over that problem really quick while I get this set up, and then we'll talk about this very briefly, okay? So read the problem 6.67. It walks you through how you could get the shape of the curve. That damn orbiting nuts hitting me in the head. Angus makes the best demos. All right, here we go. You want to check this out? Let's look at this. Ready? Here we go. I'm going to pull this thing. You see the shape starting to form? Oh my gosh, that water bottle is really close. Now, do you see the parabola shape there? Does this have any practical applications, you think, or is this just something cool to look at? Whenever I say that, there's a practical application, by the way.
Maybe the curvature.
It relates to astronomy. So I'll give you that. Yeah. It turns out you could take a giant pit of mercury, spin it like this, and the mercury basically becomes a parabolic mirror. And you can do astronomy. And it's actually described right after the problem. Interesting to note, do you see this? After part E, this is described in there. This is called a Zenith Mirror for about $10,000 and a room that basically you don't want to go in because it's filled with mercury and mercury vapor. You could actually look straight up and have a really cheap telescope that's really huge and gets really good resolution. The downside is it only looks straight up. Now, if you're curious about the shape of this, I'm just going to mention that you could do that problem in the interest of time. Why? Because I'm not putting this on the test, and I don't ever plan to put this on the test. I just think it's cool, and I thought you might like to see that. If you want to understand this, that problem is there for you. Is that good enough? I'd love to spend the time on it, but we don't have the time. All right. Let me show you another one. Look at 676 really quick. Feeling? Oh, only straight past everything up here. Whatever, it's just a physics book. 676. I mentioned this one. It's, you know, a lot of these relate to test type questions. That's why I'm trying to give you some insights so you can kind of get a feeling for them before test day. You know what I mean? Jules, are we still on?
Yeah.
Yeah, okay. All right, here we go. So in this one, we got the string pre-wound. I don't know if you can see this very well, but there's a ball here, right? Now, I don't know if you can see very well right next to my hand. There's actually two different strings here. This is not one string. This is not one string. There are two separate strings. Everybody okay with that? Why would I be mentioning that? If you were doing an FBD and this thing is spinning, how many forces are going to act on this ball when it's spinning? How many?
2T.
How many tension forces? You said 2T? Okay, I guess what I'm thinking is T1 and T2. You know what I mean? So he's saying there's two tension forces? Yes, and I would label them T1 and T2. You agree? What other forces appear on this ball? mg. What's the force that pushes it to the outside? There isn't one. What's the force that pulls it to the inside? Parts of the tension, the component. So this is tricky. Some of the tension helps balance mg. Some of the tension provides MAC. Did that make sense? So when we run this thing, right? You can see this device. Maybe you can see it a little better now. Is that showing up, Jules? Yeah. Let me go outwards and upwards, right? Just so they can see that a little bit better. Let's just run this one more time. Screw this. I'm just going to go. A little bit complicated, but at some point it might settle down. Right? Do you see it there? Can you see the strings, Jules, or not? All right. So in this case, well, you can see it right now. Which string has more tension as it gets slowly, right? As it starts rotating slowly. The upper one has to support some of the weight. So we expect the upper one to have more tension than the lower one. So that's a way you can check your answers. I highly recommend you do this problem. And in this problem, it looks like you're supposed to solve for things in terms of omega. So that's good practice. Is that pretty good on that? Yeah. All right. And then I want to get to fictitious forces. So that just gives you a visualization of problem 6.76 if you're trying to understand it. A really cool thing about this one is, as it goes faster and faster, which force becomes negligible? If this goes really fast, which force becomes negligible? mg. Think about it. MAC gets bigger and bigger as you spin this faster and faster. So as you get faster and faster, mg doesn't matter. What happens to the two tensions as you go faster and faster? No, the top one becomes more, but the bottom one also becomes more. If mg is negligible, they become approximately the same. So when you're going slowly, the weight matters. The upper one has to be significantly larger. As you go hella fast, most of the force is horizontal. mg doesn't matter much. These two are approximately the same. Did that make any sense? So I know this may seem odd, like why care about this, but imagine you're an engineer and you're building stuff, right? You might want to think, look, if you're building an engine, maybe the weight of the component itself doesn't matter that much if you're going at 6,000 to 7,000 RPMs. So sometimes the weight is completely negligible, sometimes it's not. That may simplify your analysis and make it easier to design things. So these cases that I described, what happens when the mass is large or small, sometimes that can be useful when you're designing products. Enough said. If you really want to be good at physics and engineering, things that you want to do, when you finish a problem, you can ask yourself, what if, and then just make up scenarios. And you can learn a lot that way, right? You'd be like, what if I spin it fast? What if I spin it slow? What if I make it bigger? What, I don't know. So those kinds of what if questions can help you become a better designer of products. And they can also help you really understand your physics if you're constantly asking what if. Enough on that. Okay. Fictitious forces. Give me a sec here. There we go. Now we can get this thing going. Now, this isn't going to be perfect. So let me rotate this around right here. And it's not quite the center. Okay, now I know this isn't perfect, but Jules, can you see that all right? Zoom in a little. Okay. Oh my gosh, come on. If I try to go too fast, I end up taking longer, so I gotta get this right. Oh my gosh. Yeah. I'm going to lose my freaking mind. There we go. Kind of there. Whatever. Okay. Now here's the deal. I don't know if you can see this all on Zoom, but I'll just tell you. There's a string right here. There's a hanging mast right here. You probably can't see it over on that side, but there's a hanging mast right here. So there's basically little wheels on this cart. So the little wheels basically are used to mean negligible friction. The wheels aren't going to use up much energy. So even though there is friction in the real world, these little wheels on the bottom make friction negligible. That's why we can have just this tiny little 20-gram mass move this 500-gram cart. When I remove this stopper, what's going to happen to the cart? Will it stay at rest? Will it accelerate? It's going to accelerate, right? The friction is negligible. The tension in the string is going to cause it to accelerate this way. What's going to happen to the ball? Will the ball accelerate or not? Okay, he said it's going to stay still for a bit. What do you mean by that?
There needs to be tension.
Exactly. We need tension for this ball. But let me ask you this. Will the ball move that direction ever? Will the ball ever go that way? No. Eventually, once the tension builds up, which way is this ball going to go? That way. Now imagine if you're sitting in the car. Relative to you, which way is the ball going to move? So relative to you, we imagine the ball might stay here for a split second until there's tension, then come along with it, right? So relative to you, you perceive there's a force backwards on the ball. Look at this ball right now. What direction are the forces on it? What's one force on the ball at this point? Give me a force. There's T, tension, this way. Notice it's up and that way. There's mg down, right? Again, pretend my fingers aren't there and this is moving. The idea is there's no force backwards. There's a force forwards on the ball. The perception that it moves backwards is fictitious. It appears that there's a force back on the ball. There is no force back on the ball. Good? Let's run this and see. Okay. Jules, is it still on screen? Now, keep in mind, this protractor is here just to give you an idea that in theory, you could measure the angle, right? Let's take a look. I think I taped it. Oh, there's Velcro right there. Sorry about that. Amazing. Science doesn't work. Okay, let's try this again. Ready? Oh. Now, in this case, maybe we need to make this a little more dramatic, right? Can you run around and help me? Can you just pull that to the other end? I'm just going to put on much larger mass, so this is more dramatic. And again, we only need the first like half second of motion. I'm ready for it. Jules, does it show up to about right here?
Yeah.
Okay, that's all we need to see. Let it rip. Go. Did you see the ball do just what we talked about? Okay, let's draw it on the board and analyze it. Still doing good on time. Okay. So here's what's actually happening with the ball. The ball is here. There's tension up this way. The ball we see is accelerating this direction. There's a gravitational force downwards. We're ignoring air resistance. So this is the, and by the way, which problem is this in the book? Fictitious Forces.
6.7.
6.70.
Yes.
Thank you. That is what page? 120?
Yeah.
Look at page 120 so you don't have to write anything if you don't want to watch, right? So this is, I think the ball is mass M2 in this problem, right? Yeah. Oh, no. Okay, whatever. I'll just call this mass of the ball. So how about M subscript B for the ball? So I'm looking at an FPD of the ball. Now look at this. There's going to be some angle here. This angle is theta. So what's this angle? So what's this component that I'm drawing right here? T cos or T sine? T cos. And I think that's what Jacob was talking about, right? T sine. Yep, I agree. So now, do you agree that T sine theta equals MA in the x direction? And obviously in the y direction, I think we get what? T cos minus mg, and that's the mass of the ball. I should put the mass of the ball equals mass of the ball. What's the acceleration up and down? After it's moving and kind of stabilized, what's the acceleration up and down? 0. To be clear, it's pretty complicated right as it gets started, but it rapidly kind of reaches that equilibrium angle. Is everybody okay with giving me that? It's complicated. We saw it bobble around a little bit, but if it gets stabilized, we know that's the case. Okay. Now, I'm going to show you a math trick that is pretty weird and makes me uncomfortable, but I want you to be able to understand what you might read on the internet. Let's just do a little math here and say T sine theta minus MA equals 0. Do you agree this is exactly the same statement? Now think, this is where we get fictitious forces. What if I call this the sum of forces equals 0? What we see is there'd be a force T sine theta. There'd be mg. This would have to correspond to a force pointed which way?
To the left.
To the left. This force does not exist. But if we pretend it exists and then pretend the acceleration is 0, we would get the same math. This is called a fictitious force. oh my gosh, I have to try and spell that. I have it written here. This is not a word I spell too often. Fictitious. Did I get it right this time? Gosh, that feels weird to me. I don't, something about the way it looks on the whiteboard at this angle, this makes me feel uncomfortable. So I apologize if I spelled wrong. Fictitious force this way. Now you may be saying, dude, that, I don't, this is the force you perceive pulling the ball backwards. There is no force pulling the ball backwards. Which way did the ball move? Forwards. It moved backwards relative to the car. It moves forwards relative to the earth. So sometimes saying those words relative actually adds clarity. Yes, question.
So is it useful for finding relative speeds and stuff?
Exactly. This device, take a look at this. If you tell me the angle, right? And actually look at this. Let's look at these two equations. If I take a ratio of these two equations, look what happens. Just give me a second. That's the left sides. Over here, I get look at this. If you tell me the angle, you learn the acceleration. That protractor is a device that can be used to measure acceleration. It's a meter that records acceleration. It's an accelerometer. Now, you have accelerometers in your iPhones. I don't. I have a flip phone, but look at that baby. Oh, yeah. Yeah, look at those button size. Oh, yeah. I can almost read it. Anyways, but these accelerometers can take different forms. This is the most crude accelerometer you could ever imagine. But essentially, other accelerometers could be based off other types of physics, and they're related. Is that cool? So that's why this device is brought up here. You can learn about your acceleration this way. Cool? Question or, oh, okay, yeah. Is this ever useful? It turns out, yes. The one problem we're going to do later this semester where we use these fictitious forces, this is a really cool trick. If something's accelerating, we have to do Newton's second law and do lots of math. But if we could replace the acceleration with a fictitious force pointing other way, notice, if it's accelerating to the right, the fictitious force has size ma and it points the other direction. You can take a problem from Newton's second law, F equals ma, to Newton's first law. Sum of forces equals 0. Different math tricks can be used. We're going to do a whole chapter called statics, where things aren't moving and they aren't rotating. If you replace the acceleration with a fictitious force, you can use all the techniques that we learned in chapter 12. You can find out what velocity you need to drive before the car tips instead of slips. Remember we talked about bank curves and all this? If you go too fast, the car could tip, and that relates to this fictitious force. Anyways, is that enough on that? Look at 6.72. 6.72 really quick. Imagine you're in a car, right? And there's a slippery bench seat. Let me draw a picture of it here. Let's just do this. Okay. So imagine you're in a car in a slippery bench seat, right? And you're going around on a flat curve. There's an axis over here for the center of the turn, right? Do you agree that if you're sitting in this car, if you're a block sitting here in this car, right, there's a normal force up, there's mg down, you need to accelerate this way, agreed? Well, that gives rise to this fictitious force the other way. This does not exist. But this is the force you perceive that's pushing you to the outside of the turn when you turn. Good? You ready for a little puzzle to finish the day? Anyways, yeah, I just wanted, any questions about this? Oh, this is why if you're sitting there, you like if you had this block sitting here, as you turn, as you're going around this turn, you'd see things sliding to the outside. Really what's happening is they're moving in a straight line and the car is sliding underneath them until they hit the wall, and then the thing goes in circular motion. All right, all right. Great. See the next problem where it says fishing for direction? Read that one. 673, fishing for direction. Let me get the camera on it. Water bottle out of the way. This crap out of the way. All right. Here's the problem right here. I got these two peanut butter jars inverted. Can you imagine Angus having to clean out these peanut butter jars? No, I make him do some weird stuff, don't I? Anyways, and then he had to figure out how to get these pool floats in here. So he got some string and he glued that to there and then filled these up and flipped them. My question is simple. When I spin this thing, which way are the pool floats going to go? Are they going to go towards the outside or towards the inside? What is your intuition tell you? And then what do you know about physics with me?
We're never right.
Ready? Oh boy, any more of the Velcro is going to break. Which way are the pool floats going? Towards the outside or towards the inside? Oh, man, this one's like tipping over, right? Okay, so in this case, I don't know if this is making any sense or if it's even showing up at all. Oh shoot, did one of the strings just break? I think one of the strings just broke. Crap, this is a tough demo to do. Look at this one. Did you see this one? Oh no, there's good. Let me get my string so I can pull this smoothly. Sorry. I get into this stuff, right? This is basically a model of a centrifuge. Do you agree? Now think about this. From a fictitious force standpoint, what direction is this thing accelerating, this pool float? Which direction is it accelerating as it moves in circular motion? Towards the center. Acceleration is towards the center, right? So that means there's a fictitious force outwards, okay? We could think of that as artificial gravity, right? So there's artificial gravity towards the outside. Which way do pool floats go relative to gravity? Opposite. So what's happening is we're going to introduce a fictitious force outwards, artificial gravity. That's what a centrifuge is doing, which means the pool float should go towards the inside. Opposite gravity, opposite fake gravity, right? Or when you do a centrifuge, the heavy stuff settles out to the outside, the light stuff goes to the inside. All right, let's try it one more time if I could actually do this right. Isn't that cool? Oh my gosh. You guys like this stuff or not?
Yeah.
I find it very interesting and I hope you can enjoy it some. Oh my gosh, this is really today. There we go. Come on now. Hopefully that's enough here. All right, you ready? Let's see if I can pull this smoothly so we can see the effect better. Oh shoot. Oh. Look at that. Oh my gosh, it's not quite working well because I think I went too fast. It's got to be just the right speed. Maybe if we let some friction gradually slow it down. I don't know. Do you see that at all? That's what we're trying to see there. Sometimes it works, sometimes it doesn't. It's getting a little bit weird because the water level has to be just right for you to see this effect. But anyways, all right, that's pretty cool. That's fictitious forces. So far, so good? All right. That is all of chapter 6. Did you notice we spent a lot of time on coordinate systems today? Look at page 123. If you look at page 123, because we still got 3 minutes here, it's just right for this. If you want to practice with different coordinate systems, just so you get used to dealing with them, page 123 shows you 4 different choices of coordinate systems and 4 different ways to label the accelerations. It discusses whether the accelerations are positive or negative. On the next page, page 124, are the answers. So you could, if you're wanting to learn about plus minus signs, you can do that. All right. If you look at page 125, now you could see the ball on the string, and I mentioned I would talk about this. You could see all the different options. You could do radial coordinates, centripetal coordinates. If you're wanting to learn about the ball on a string in different coordinate systems, you could do that. And again, the equations and the minus signs associated with those choices are shown on page 126. Got it? So if you want to learn about coordinate systems, do that. Okay, practice your brains out. We're starting chapter 7 next time. All right, I'll see you in lab tomorrow. I'll send the lab manual soon. We're basically doing a lot of friction problems. If you can do one thing for me, do the FBDs for the lab manual. There's going to be 3 cases. If you do the FBDs and come into class and you already know them and know the force equations, you have a chance of getting out of lab on time. If not, you're going to have to leave and do a lot of work at home. So do the FBDs after I send you the lab manual. Okay, that's it. That's it. Woo! That's intense. Oh. You're just raring to go, huh?